So I started the recording, and welcome to Electronic Algebraic K-theory seminar. Today we are very happy to have Lennart Meier, who will talk about the chromatic behavior of algebraic K-theory.
Yeah, thank you very much for the opportunity to speak here. So I will speak about a joint project with Markus Land and Georg Tamme. And I also want to add that we profited a lot with from discussion with Keio, Matthew, and Dustin Clausen on this. I just want to mention this right away. Okay, so let me start with a bit of motivation. So many of our most powerful invariants of rings or schemes transform characteristic P into characteristic 0. So, for example, Ital cohomology does this, or crystalline cohomology. Theories of this flavor, which I totally don't want to talk about today. What I will talk about today is mainly K-theory, so algebraic K-theory, but also TC and TP have the same flavor, and I guess there are also other theories you might define. Just as a short illustration, so the archetypical example of something characteristic P is Fp. So let's compare 3 different invariants of rings on the example of Fp. So there's THH of Fp. So which I view as a spectrum here. So take the homotopy groups. It's a polynomial ring in one variable. So this does not transform characteristic P into characteristic 0, but it just stays characteristic P. So this is something I don't want. So while if I take TP, I get ZP x plus minus 1. So if you don't know what TP is, don't worry. It's just one example. And I will mostly focus on K-theory later. So this would be also a characteristic 0. And here I will P-complete this to make this of the same quality. This is just ZP concentrated in degree 0. So which means equivalently that this is the same as HZP. So sometimes I will leave out, so the H stands for Einstein plane spectrum. Sometimes I will leave this out, sometimes I will write it. I hope this won't lead to any confusion. And as you all know, this last computation is due to Köln. Okay. So in other words, we can say so if E is K-theory, TC, or TP, might expect that E of R inverted P is non-zero, even if R inverted P is 0. Okay. So, and the point now I want to make is that in chromatic homotopy theory, inverting P is just the first, or we might say 0th step of a whole hierarchy of things one might do. So in chromatic homotopy theory, inverting P is just the 0th step in a whole hierarchy. Okay, so let me explain what I mean. So let here E be any spectrum which might be the K-theory of some ring, for example, or might be anything you like. So then on the one hand side, I can associate to this P inverted, what I just said. Okay. On the other hand, I can try to capture everything which is not seen by inverting P. And in some sense, this is done by just quotienting by P. So I have multiplication by P map on the spectrum. I can just take the cofiber of this. Or if you want, you can also write this E tensor, the sphere spectrum mod P, which is also called the mod P Moore spectrum. Okay. So to see what one should do in the next step, it's maybe good to contemplate why we actually did this, inverting P and taking mod P. So let's just write this as E tensor the sphere spectrum. The sphere spectrum monoidal unit, you can just write it like this. So if we want to invert an element, it should be better an element which is non-nilpotent. And there are not so many non-nilpotent self-map of the sphere. So the non-nilpotent self-maps of the sphere are exactly the maps multiplication by n for n non-zero. So in some sense, okay, we might invert another integer than just P, but essentially the only thing we can do is inverting P or inverting product of primes. If we want to do it for all spectra at once, so for the sphere spectrum. Okay. So it turns out now that S mod P has an essentially unique self-map called V1, which was found by Adams. So strictly speaking, it's a graded self-map, so it has a positive degree. So slightly screwed up my picture, but I do it like this. So now I can do, again, two things. So I can look at E tensor S mod P V1 inverted. So this one possibility, or I can look at everything not seen by this process, which is just quotienting also by V1. Okay, and now you might already see the pattern, namely actually it goes on like this. So there's again an essentially unique non-nilpotent self-map V2 of this guy. So I can form mod P V1, V2 inverted, or I can quotient further. And this goes on like this. So this is that these non-nilpotent self-maps exist and are essentially unique for arbitrary n. So this goes on like this. It's a theorem due to Devinats, Hopkins, and Smith. Or I guess the theorem itself is due to Hopkins and Smith, but it's crucially based on work of the three of them. It's called the periodicity theorem. This is what's behind these things. So in this sense, inverting P is just a zeroth step in a whole hierarchy. So to abbreviate things a little bit, let's give a name to this. So we might abbreviate like this. So the T is called telescope for mostly historic reasons. So this is where the T comes from. So this motivates that we should consider E tensor Tn for all n. Where T0 would be just inverting P. Sometimes people also use different notation, but this is what I will use here. Okay, so so I just want to say that there's also a process of localizing a spectrum at Tn instead of tensoring with Tn. And I want to say that this is 0 is the same as the Tn tensor S is 0. And I define this to mean that the height E is bigger or equal to n. So in other words,
sorry, Lennart, you mean the E, not the sphere?
Oh yes, thank you. I mean, yes. So in other words, the height of a spectrum is the maximal n such that T n tensor E sorry, I mean here non-zero also. Sorry. Okay, this is what I mean. That this is non-zero. So we set the height of E to be -1 if T of n tensor E is 0 for all n, and infinity if it's non-zero for all n, or if non-zero for arbitrary high n. Okay. So let me give you some examples. So so what is the height of an Einberg lane spectrum, HR? Well, it turns out that Tn tensor HR is 0 for all n bigger or equal to 1. So the reason behind this is essentially that, let's look at T1 tensor HR, the same as HR mod P, V1 inverse. And this V1 here, I mentioned this as positive degree. It's an element of positive degree, while the Einberg lane spectrum is concentrated in a single degree. So if I invert something positive degree, it will be 0. And the reasoning is similar for higher n. So this means the height can be at most 0. And essentially by definition, we have that it's -1 if R is in characteristic P in this sense, and 0. So we have this. So, and let me give you some further examples that there are also spectra of higher height. So for example, we might look at complex K theory. This has height 1. And the height of the sphere spectrum would be infinity. So these are some basic examples. And I want to mention a statement which says that the height actually behaves a little bit nicer than what you might expect, maybe. It's a theorem due to Matthew Naumann Noel and to Jeremy Hahn. So, namely, that if E is an E infinity ring spectrum, So this means like a very commutative ring spectrum. If you're not so familiar with this terminology, then Ti tensor E is 0 implies Ti plus 1 tensor E is 0. So this means that so a priori, if you have some spectrum E, you might imagine, if I draw as blocks the things where Ti is non-zero, you might say, for example, T0 tensor E might be non-zero, T3 tensor E might be non-zero, and T7 tensor E might be non-zero. And then you say, okay, the height is 7. But actually, for an E infinity ring spectrum, such nonsense cannot happen. But if the T7 tensor E is non-zero, then this must be also true for all the lower Ti. So, and in particular, and this is the original theorem of Matthew Naumann-Noel here, is that if E inverted P is 0, then Ti tensor E is 0 for all I. Okay. So note, I did not say this, that I secretly always fix the prime P here. And this spectra Ti only makes sense if we fix the prime P. So this is what I want to say about height in general. And in particular, the earlier statement can be, so with earlier statement, I mean the one which I've been a while ago, namely this one, can be now rephrased as if the height of, just write as the Algebraic lane spectrum to be clear, is -1, which means that R inverted P is 0. Or I should say, even if we might expect that some invariant of this guy might have height bigger or equal to 0, which means, in particular, that this is non-zero. Okay. So are there any questions so far about this notion of a height and so on? Oh, sorry. Okay. So maybe I move on then. So this expectation here can be actually generalized considerably. Namely, there's a so-called Redshift Velocity. And before I write it down, I want to comment on the word red here. Namely, redshift means in chromatic homotopy theory that something increases in height. This is it's based on similar analogies as kind of the wording chromatic homotopy theory. Maybe I don't want to explain this now in detail, but redshift always means increases height, so the n increases. So the redshift philosophy means, in one of its more extreme incarnations, so for an arbitrary E infinity ring spectrum R, we have the height of K of R is the height of R plus 1. So said, this is no one really expects this to be true in this generality, in particular, as I will present a counterexample in a few minutes. But I think it's expected to be true quite often, and maybe under some mild additional hypotheses, but it's very far from proven in general. But let me give you a few examples to convince you that it's not just total bogus. Okay, so one example we already saw. So HFP has height 0, while K of FP, and it's just P complete because it doesn't change the notion of height, is HCP, and this has height 1. So this is check. The case of R equals HZ is due to Mitchell. So he showed the height of the K theory of Z is 1. And where the theorem really became more interesting, the kind of conjecture actually became plausible is due to work of Rosoni-Rogness, where they showed that the height of the K theory now becomes slightly confusing. Take the K theory of complex K theory, the height is 2. I think strictly speaking, they only show it for primes bigger or equal to 5. But I think no one believes it would be wrong in primes 2 and 3. So these are the main examples where the conjecture is fully known. So I should say that actually, I would say in this redshift philosophy, on this redshift conjecture, there are two different statements of quite different flavor. And I mean, equality can be seen as consisting of two inequalities, namely smaller equal and bigger equal. And bounding the height from above is usually approachable and more conceptual techniques, while bounding it from below usually uses some calculational techniques, at least so far. At least in the case of Rosoni-Rogness. So, say bounding the height from above is known in many more cases. So, for example, let me give you a more or less trivial example first. It's known for all FP algebras. So, why is this? So say this is K FP algebra R, then K of R is a K of FP module. And this implies that the height of K of R is smaller or equal than the height of K of FP, which is 0. So it's automatically known for these. So this way you can often, if you have one thing, you can prove it for all modules over this often. It's not quite true, but yeah, it's not quite true, but you can at least provide some bound. So, and what are more examples? There are spectra called, so it's true for Ku, also if the primes are 2 and 3. It's true for so-called spectra BPN if they are infinite, E infinity, which is not true in general, but in some cases. It's true for TMF, at least at the prime 2. This is due to, let me give some names here. This is Angelini, Knoll, and Endosalk. And the TMF case in Ku if P is 2 or 3 is due to Clausen, Matthew, now Manuel. And they also produce something for more E theories, and there's also work by Angelini, Knoll, and Quigley, where they show something. I see Jon is commenting on why it's called Redshift. So yeah, I think he has the definite opinion about this because he coined the word. Okay, so yeah, so this upper bound is known in many cases, but there are not so many very general theorems about this. More like the specific families of examples where one could prove something. And as I said, the upper bound is, sorry, the lower bound, this big or equal sign is mostly known in the cases I just wrote down. And let me just, I think I have the time to just present you the counterexample where it's not true. So it's not always true. This is an example I heard from Aki and Matthew after I gave a talk, but might have also been known to some other people. So let's take the Tate construction on HF2. So this has height -1. So if we invert 2, it's 0. So it turns out that modules over the Tate construction, sorry, this is not what I want to write. We take modules over the Tate construction and the homotopy category of this, which is the kind of, if you take the compact object of this is, okay, I'm not phrasing this very well. Let me just write down what I want to write down. Turns out that the modules over the Tate construction are the same as the stable module category. So, and the stable module category has one feature, namely it's built from F2, C2 modules, but we set things which are projective to 0. This is essentially how the stable module category is built. So in particular, the short exact sequence F2 to F2, C2 to F2 implies that 2 times the class of F2 is 0 in the K0 group of the stable module category, and hence in the K theory of HF2 TC2. Okay, and this implies in particular that this is 0, so the height of this is also -1, in contradiction with the most general form one could use for the redshift conjecture. I'm using the trivial C2 action on HF2. So I must say this example I find very nice, but a slightly curious feature here is that actually the Tate construction usually is meant to shift height down by 1. It's in some sense just not possible in this case because it's already height -1. So in some sense, the height of the K theory of the Tate construction in general should be the same as the height of the original guy. But in this case, the kind of the shifting down didn't work because it was already at the bottom. So the shifting up also didn't give the correct result. This is, of course, very vague, but yeah, just what I want to say about this. Yeah, I think, okay, there are several questions. So yeah, in some sense, I think it's an interaction of red and blue shift here, but I cannot claim that I really understand it. I think it's essentially Tate's construction blue shift, so decrease height, and K theory should increase height. But how this exactly, I mean, in this case, it's just a calculation. What happens in general, I don't know. So Sean asked, does this hold in any examples? Or is that known to hold in any examples? I'm not sure what that is. Maybe Sean can specify this. Then I could answer this. I'm not sure whether it's true that, I'm not sure whether it's known in any examples that the height of the K-theory of the tail construction original height, but it might be deducible in some cases. Maybe one can go back to this point later. Okay. So I think it's a good moment to state the first theorem I want to present. It's due to Georg, Markus, and myself. Namely, we provide about this this redshift, namely the smaller or equal part. So, namely, we show if height of R, so maybe I phrase it more specifically. So let R be an E infinity ring spectrum. So if height of R is -1 or 0, then indeed the height of the K-theory spectrum is smaller or equal height of R plus 1. So it shows in generality the one inequality for low heights. So I note, as I said earlier, height of R -1 is if it's E infinity equivalent to by this theorem of Matthew, Naumann, and Noel. And that the height of R0 is equivalent to that this is non-zero, but the T1 localization of R0. Okay, so let me give some examples. Before I give an example, I'll make one remark. So this version of chromatic homotopy theory which I presented is slightly less known than another version using Morava K-theories instead of the Tn. And I just want to say that for n equals 1, this T1 localization is the same as so-called K1 localization, where K1 denotes, at least essentially, the spectrum complex K-theory modulo P. And I think I will phrase the n equals 1 results from now on using the K1 instead of the T1 notation, because this is the one which is more commonly used and more known to people, I think. And in this case, it's just the same. And I should say this is a quite non-trivial theorem. This is the so-called telescope conjecture for n equals 1. So there's a conjecture called the telescope conjecture that Tn localization in general is the same as Kn localization. But this is wide open, and many people believe it to be false. But for n equals 1, it's known due to Mahowald and Miller. So, okay, now it's time for an example of our theorem. So there's a question. This thing with the stable model category and the tail construction is true for all rings. I think I'm not quite sure how one should exactly I'm not quite sure whether it's true in complete generality. It's certainly true for a field of characteristic 2. In complete generality, I'm not sure. Maybe yes, but I don't know. Okay, so let's do an example. Namely, the claim that the K-theory you take the K theory of Z mod P to the N and K1 localized, this is 0. So, and this is just direct consequence of the theorem I just raised, because this thing has height -1. So we obtain that this has height smaller or equal to 0, or actually, so you easily see it's equal to 0 then. And this implies that the K1 localization is 0. So this theorem has also been known a little bit earlier, actually, to Bud, Klaus, and Matthew, with a completely different approach to this, using TC and the calculation in prismatic cohomology. And there's even a more recent paper which reproves this again due to Akil Matthew, where he uses TR to show the same result. So now we have 3 different ways. And I want to mention that this actually is, this implies that K theory, K1 local K theory, has quite remarkable properties. So a consequence, and I'm allowed to say that these are remarkable because the theorem is not originally due to us, we just reproved it. So and these consequences have also been all known to Bhargav, Dustin, and Akil, that K1 local K theory is insensitive to inverting P. For all rings R. And just we mark about this, that if P is invertible, plus some other niceness hypothesis, then actually the K1 local K theory of R is equivalent to the p-adic K theory for n sufficiently large. So apart from some low degrees, the K1 local K theory actually sees all of p-adic K theory if P is invertible. But this is, this consequence I just wrote down shows essentially we cannot expect anything like this if P is not invertible, because K1 local K theory is insensitive to inverting P. To Jeremy, these are classical rings R for the moment, but actually this is true more general, and we see something about this in a moment. And there's not another question if we can bound the order of nilpotence for V1, and in our approach this is totally inexplicit. And I should say this remark is based on quite complicated work, namely it's at the end based on the norm residue theorem due to Rost and Wojcicki. And if you want to read about this, you should look at the article of Clausen and Matthew about étale K theory, where they have given very nice treatment. So, and another consequence is that K local K theory is also homotopy invariant. And this actually follows from the thing above, because as this is known by table, if P is invertible in R and we P complete. So, and K1 localization automatically completes, so it's known if P is invertible, and by the thing I just wrote down the first consequence, we are allowed to invert everywhere. Okay, so, and we can actually generalize these two ring spectra are satisfying, that the K1 localization vanishes, then these are still true. So I'm not sure whether one can say, so I don't know what happens higher the homotopy invariance. I think we can say something, but I don't think we know it in general. Okay, so let me give one more example, and then it's time for the break. So we can look at the n-truncated sphere spectrum. So this means we just have we kill all homotopy groups above n. So we just have homotopy groups in the range from 0 to n in the sphere. So it turns out that the height of this is 0, essentially for the same reason I gave for Algebraic lane spectra, that if we invert an element of positive degree on a truncated spectrum, this will always be 0. And so this Ti tensored with the truncated sphere spectrum are 0 for all I bigger or equal to 1. So, and we obtain from our theorem that the height is small 1, or actually it's not very hard to show the height 1. Because it maps to K theory of Z, which in turn map to complex K theory. And this is one way to show the height actually equal 1. One knows is smaller equal to 1. And so if R is connective, so i.e. pi star R is 0, or small, it receives a ring map for some truncated sphere. And this way we can also then see that the height, the K theory of R, is also smaller equal to, because if we localize the K theory of the truncated sphere spectrum at some Ti for E bigger or equal to 2, it becomes 0. So if it has a ring map from this to some K theory, Ti localized of K theory of R, the target also must be 0. Okay, I think it's time now for the break.
Thank you very much for the first half of your talk. There may be more questions. Okay, maybe people will ask in the break. So I will divide then all of you in some breakout rooms, and Lennart will continue his talk in half an hour, so at 1:15, whatever hour it is in your country. So let me pause recording.
Interruption. Okay, let me quickly recap what we did so far. So go quickly through this again. So at the beginning, I talked about how if we have something characteristic P, K-theory produces something which is no longer of characteristic P. So, and then I said this is a special case of a much more general philosophy, namely that we expect where is it? That K-theory shifts height by 1. It always increases height by 1. So maybe not quite always, but at least very often, and gave a number of examples. And then I said that we can actually show, in this joint work with Georg and Markus, that if the height of our ring spectrum is very low, that it shifts height at most by 1 at least. And in many cases, you can then show it actually shifts height precisely by 1. And then the main example is maybe one of the simple, it's already interesting but simple example is K-theory of z mod p to the n. If you K1 localized becomes 0. And this implied that K1 local K-theory has this nice property. It's insensitive to inverting P, and it's homotopy invariant. And then I gave the second example that if we have a truncated sphere spectrum, then the height of this truncated sphere spectrum is 0. So the height of the K-theory of the truncated sphere spectrum is 1. Okay. So in the second half, I want to tell you what is behind this kind of redshift theorem we prove, and yeah, kind of how we do this, and what properties of K-theory we use. Okay, so second part. So as a motivation, start with the theorem of Waldhausen. Which in some sense deals with the 0 situation. So that R to S the homomorphism of ring spectra. I should say, when I say ring spectra, I will usually mean what's called E1 ring spectra, what's also called, or what's also known A infinity ring spectra. So the homotopy cohesion of the ring. Of on we also earlier R and S.
I think we can't see what you're writing now. Oh, sorry. It's
apparently
okay.
there's quite some lag involved. Okay. Okay, now it's there. So the isomorphism of pi0 and R and S are also connected. Assume further that R to S is a rational equivalence. Then K of R to K of S is also a rational equivalence. And standard example is, say we want to compute the rational K-theory of the spectrum. It's interesting for a variety of reasons, some coming from geometric topology. So we have a map from the sphere spectrum to the integers by just truncating everything above the degree 0. And it's an old theorem of Serre that all the stable homotopy groups above degree 0 are rationally trivial. So this is the rational equivalence. So we obtain that this is the rationalized K-theory of Z, and this is known due to work of Borel. And actually, if we want to, we can also replace the rational equivalency by a bunch of other things. So we might also replace, can replace rational equivalence by, for example, a Z1/P equivalence in the theorem. And this is the same equivalent to a T0 equivalent. The definition was just the sphere spectrum with P inverted. This already gives us a lead to what I want to say next, namely theorem by Markus and Georg is that there is a similar theorem which is also true in higher heights. So let R to S. Okay, so what do we need? It should be n connective. I will recall in a moment what this means. Map of connective ring spectra. So if R to S is a TI equivalence for all I between 0 and n, then the same is true for the K theory of R to the K theory of S. So, and here, spectra S is n connective. The equivalent homotopy group is equal to n. Okay. So, and I want to stress that this theorem really, so it maybe looks a little bit different than you might think. So one thing is compared to Waldhausen theorem. So Waldhausen just demanded an isomorphism by 0. So it's maybe not surprising that you want to prove corresponding theorem for higher heights. We have to demand a little bit more. Here we demand it's n connective. So in Waldhausen's case would be more like 1 connective or 0 connective. And the other thing is, which might be a little bit more surprising, is that we don't just phrase it for Tn equivalence, but we really want to have T0 up to Tn equivalence. But this is the result we prove. Okay, so let me give you a very short sketch of the proof. Actually, it's the same sketch you can also go for Waldhausen's theorem. So we use the plus construction model for K theory. So omega infinity of K of R is equivalent to BG infinity R in the plus construction. So this, of course, a very classical construction in the case of rings, but you can also do it for connective ring spectra. Just for non-connective ring spectra, it's not what you want, but for connective ring spectra, it's the correct result. So, so the steps are as follows. So with assumptions, as in the theorem, BGL infinity R to BGL infinity S is a T0 up to Tn equivalence. By the way, I think I did not say this, but maybe it's understood that if I say Tn equivalence, I mean it's equivalence after tensoring with Tn or equivalently in after Tn localizing. So this is, I think, the most difficult step of the theorem. And this uses work of Bausfield and of Kameli, Schlank, Janowski. So it's really what we're using is not work about K-theory or something like this. It's really something about unstable chromatic homotopy theory. And I think I don't want to say more about this, but I mean, what we do is maybe not particularly deep, but we use, I think, quite non-trivial input for unstable chromatic homotopy theory. Then there's the easy part, namely, if you apply the plus construction, this is a Ti equivalence for all I. Why is this? Because the map into plus construction is equivalence in all homology theories, regardless what homology theory you take. So what we obtain from here is that BGL infinity R plus to BGL infinity S plus is a T0 to Tn equivalence. And then the last step is that omega infinity detects Ti equivalences. So this is a remarkable feature about this. So this is for I bigger or equal to 1. This is a remarkable feature about this Ti localization Ti equivalence, and this uses the Bausfield-Kuhn functor. So if you know what this is, you might be happy with this. If you don't know, I just say it's another non-trivial ingredient from chromatic homotopy theory. So kind of this is actually something we also learned from Keio Matthew. Okay, so this is in short how the proof goes. So are there questions about this? Okay, and this first point is also where we really use this thing that we have a T0 up to Tn equivalence. So, and I want to remark that same theorem is true without T0 if R to S is n plus 1 connective. So we can also just work with T1 to Tn instead of T0 to Tn by just, so if you compare, here we have n connective. If we go one further, then we have this also. Okay, and maybe I should, I said we need it for the proof, this T0 to Tn, but I should say, so it is not true. Warning. So if we have Ku to so to some truncation of Ku, this induces T2, sorry, this is a T2 equivalence. As both sides are T2 acyclic, as you can show. But if we take K theory of Ku to K theory this thing, then we have this thing is 0. This actually follows from what I said earlier, that if we have a truncated ring spectrum, then the height is at most 1 of the K theory, while this is non-zero by Ozoni-Rogness. So if you just formulate for T2, for example, without T1, then this theorem is just not true, regardless how connective the map is, because you can make n arbitrary large. Okay. So let's apply this to, in some sense, the most important example for us is the following. So let's apply this. Let's apply our theorem to R goes to pi 0 R, or I'm the lane spectrum of this, if R is connected. So this is a one connective map. So what we obtain from this is that obtain the following: K1 local K theory is truncating. And K1 is cyclic ring spectra. I.e., if the K1 localization of K of R is 0, then K1 localization of K theory of R is the same as of its pi 0. And I will just give you the proof if pi 1 of R is 0, and one has to work harder if pi 1 of R is non-zero. Okay. So if pi 1 of R is 0, then actually R to H pi 0 R is actually 2 connective, which makes our life easier. Okay, it's the worst thing. Other thing is that R to H pi 0 R is a K1 equivalence, or equivalent T1 equivalence. Yeah, thank you. This should be this. Okay. T1 equivalence, because both are K1 acyclic. So R is K1 acyclic by assumption, and the Algebraic lane spectra are always K1 acyclic. So by theorem, we exactly get what we want. Okay. So, and luckily, so there's a very nice article by Marcus and Georg about excision in K theory. And one thing they show is that truncating invariants are always Neal invariant. So in our case, this means that so if R is a classical ring and I in R is a nilpotent two-sided ideal, then then the K-theory is insensitive to quotienting by this nilpotent ideal. So I guess one has to be a little bit careful because our invariant is not truncated in general, but just on K1 as cyclic spectra. But this turns out to be not a problem because every HZ algebra is K1 as cyclic. Particularly every plane spectra of every ring is K1 as cyclic. Okay. So example. So we can look at the K1 over K theory of Z mod P to the N. Well, by what I just said, it's the same as the K theory, K1 localized of FP. And we know that this is HZP, if we P complete. So maybe let's write it differently, not to lie. So this is the same as the K theory of HZP, which is 0. So this is how we prove this this theorem of Butt, Clausen, and Matthew. How we reprove this? This actually this was the starting point of the whole project. We want to reprove this theorem using this Land and Tamme theorem. Okay. So are there questions about this? Okay. So, and let me now tell you how to, there's a question by Sean. So Sean asked about, can we apply this to cochains on a space? And I mean, as he always says, this is not connective, and I don't think we can directly apply this because it's really about connective things, and we truncate this. And about co-connective things, I think we can say less at this point. And there's another question whether this is enough to get CDH descent, and I think the answer is yes, we get CDH descent. But if you want to know what precise descent things we get, it's also very nice to look at Aki Matthews' recent paper where about K1 local TR. He has a very nice section about this. And there's a question by John Klein whether Land Tamme result passes through the TC world, and the answer is no. This they have a very general framework. They work really with localizing invariants of stable infinity categories, and they can apply it to TC. They can apply this to K theory, but this does not use. If you want to apply to K theory, it does not use TC. Actually, none of the results, as said, uses TC in any way. For example, this result I mentioned about that K theory preserves chromatic equivalences. This is really proven on the K theory side. Actually, you can deduce the corresponding result from TC from this by the Dundas-McCarthy theorem, but actually don't know a direct proof for TC about this. So, and then there's a question about TR, but I don't quite understand, but it's just said, but true for TR. Probably whether the Land Tamme result is also true for TR. I must say I know very little about TR. So if TR is also a localizing invariant, then the part is that if it's truncating, then it's nil invariant is certainly also true for TR. But okay, and Aki says Land Tamme proves that truncating invariants always satisfy CDH descent. I just also noticed that I slightly formulated this misleadingly. So the first part is between Land and Tamme that truncating invariants are always nil invariant, and the other thing was specialization in this case, which is in our joint paper. Okay, so what else did I want to say? Right. I want to come back to this redshift style results I talked about earlier. So we call the earlier theorem that if R is E infinity and R1 over P is 0, so equivalently height of R is -1, then the height of the K-theory of R small equal to 0, or what's equivalent by the theory of theorem of Jeremy Hahn, that the K1 localization of K of R is 0. Okay, so let's prove this. So it suffices to show that the K1 localization, the K-theory of the connected cover of R, is 0, as the K1 localization of K-theory of R is a modulo over it. So this means we can assume that R is connective. So because the height of R is -1, it follows that K1 localization of R is 0. So this implies, so it's K1 acyclic. This means that it's truncating. So we get that its K1 local K-theory is the same as of its pi 0. Okay. So as R 1 over P is 0, it follows that pi 0 R 1 over P is 0. So it follows that pi 0 R is a z mod P to the n module for some n. So from this it follows that K1 local K-theory of pi 0 of R is a module over the K1 localization, the K-theory of z mod P to the n, which I argued above is 0. So this completes the proof. So this is the case of going from height -1 to height 0. On the other case, I just want to shortly comment. So more generally, one can show that Tn local K-theory is truncating on T1 to Tn acyclic ring spectra. So, and you can use the n equals 2 case to also show that if the height of R is 0, then it follows that the height of K of R is small equal to 1. But I don't want to give the details, but it's not very hard from what I just said. Okay, and so now I want to go back to one point I mentioned earlier. So in first part, I meant that if we have R is a is a ring, so not a ring spectrum, but a ring, then K1 local K theory is insensitive to inverting P. So more general, if R is a connective, K1 is cyclic ring spectrum, I can now do the following. So I forgot to write equivalence. So if I have the K1 local K theory of R and the K1 local K theory of R1 over P, I can use that it's truncating and this I know to be equivalent by what I said before. So I see that it's also insensitive to inverting P on all connective K1 acyclic ring spectra, not just on classical rings. Okay. So are there questions about this? Okay, so these are some things we know. So next I want to talk about a question where we only have a partial answer. So question. Is there a version of, so I didn't give the theorem a name, so I just say of theorem star, and I give star this in a moment, without connectivity. Sometimes this is also, you can say about what Sean asked. He asked about a co-connective example. So this would be star. So if you have an n-connective map, then it preserves these chromatic equivalences. And we can ask, is it necessary that the map is n-connective? Is it necessary that the ring spectra are connective? And we actually don't think we have a good counterexample why this is totally necessary. If we're talking about TI equivalence for I bigger or equal to 1. And let me formulate a more precise version of the question. So more precisely, is it always true that if R to S is a T0 to Tn equivalence, that Kr to Ks is a T1 to Tn equivalence? So I left out the T0 because if we ask about T0, I think they're pretty easy counterexamples. So just about T1 to Tn. Equivalently, there's a universal case if we leave out connectivity. Namely, we can just map it into the localization. We can ask, is this a T1 to Tn equivalence? So let me look at a special case first. So assume R is T1 to Tn acyclic, e.g. R is a classical ring. Then this big localization here is just the same as inverting P. Okay. And here we know, so we know that K of R to k of r 1 over p is T1 equivalence. This is something I mentioned earlier, or equivalent to K1 equivalence. And if R is a classical ring, we certainly also know it's Ti equivalence for all I because these would banish these localizations. But actually, we can also give more examples. So let's R be a Ko module. So Ko is connective with K theory. So what are examples of Ko modules? So e.g., we might take R to be complex connective K theory, complex periodic K theory, or any Z module. Because we have a map from Ko to Z, a ring map, so every Z algebra is also Ko algebra. So here it turns out that we can calculate this localization. So first of all, it's again so that this is T2 to Tn is cyclic, so we can throw out all higher Ti here, of T0 and T1, and this fits into the easy fiber square. So here we invert P, here we invert the bot element, and here we invert both. And we have this fiber square. And actually we can show that the question, so this theorem 2s3 question has positive answer. For Ko algebras. So that means for Ko algebras, we know that these connectivity assumptions are just not necessary. Yeah, so sadly, we don't quite know it in general. So I think I want to end with saying at least one more thing about these localizations in general. So in general, for an MU module R, there's a nice description of this localization. And I will just phrase it a little bit vaguely. Localization of R corresponds to the complement of the vanishing locus these things on spec pi 0 of R. So what does it mean? So let's assume this P local, else it doesn't really make sense maybe. So we have elements P v1 to vn in pi star mu localized at P. And maybe it's not just a module. If I phrase like this, should be an algebra. So we can map them to pi star of R. So we have these elements which control the heights of ring spectra. And we can look at the complement of the common vanishing locus. This is an open subset of spec. Yeah, so I guess I should write spec pi star of R. Of spec pi star of R. And there's a spectral sequence. It's one way to phrase a spectral sequence going from the cohomology groups of this open subset to the homotopy groups of this localization. So in this sense, it corresponds to that. But you also might see it in a spectral way that you can write it. You can define a sheaf of ring spectra on spec of pi star R, and this would be exactly what we have on this open. So what I want to say now is that this thing has a high codimension. So at least if we are a nice case where this is a regular sequence, the codimension would be n+1. So what we are asking then, if we, let me scroll again, if we compare the K-theory of R with the K-theory of this localization is whether removing this thing of high codimension changes the localizations of K-theory. So in this sense, so let's call this thing U. So one might say that we're asking whether K-theory of R, K-theory of U is an equivalence. And things are called a pure equation. Because, for example, we know the Brauer group of a scheme doesn't change if we remove something in codimension 2 or higher. And I think this has a little bit of a similar feel. So I just gave this a little bit more precise perspective on this for MU algebras, but I just saw that Sean asked a good question in the comments, the chat. Namely, there's a more general perspective on this. And actually, this is also something we write down in the article if you want to look at this. So if you have something which is not an MU algebra, we cannot directly have these elements VI and so, but we can think about the Balmer spectrum of the category of spectra. So if you know what this means, it's good. If you don't, you just ignore the content and have a similar perspective there that we look at a certain subset, this localization corresponds to a certain open subset we might consider. And then one might consider it like a purity statement with respect to the Balmer spectrum. Okay, I think this is everything I want to say, and I thank you again very much for listening.
Thank you very much, Lennart, for a very beautiful talk. Let's unmute ourselves and thank Lennart. Are there more questions? Actually, I have a question. Maybe I missed it, or did you say something about why Keio appears in your? So you said that that question holds for Keio algebras. Why Keio?
One property of Keio, I mean, this is, I must say, in some sense, this is an example, just an example where we can prove it. And we wanted to generalize it from the case of Z algebras where we knew it before. And every Z algebra is a Keio algebra, so we thought this might be a natural generalization. But the property we really use is that Z is a finite Keio module. So in general, if you have some connected ring spectrum, usually if we take its pi 0 is not a compact or perfect. I think perfect is the term which is maybe most known here, not a perfect module over the ring spectrum. So you can usually not build it in finitely many steps. But for Keio, it's possible. I mean, it's like a regularity condition, if you want, that you can build the residue field, and the residue field Z is perfect. And for Keio, I can just, maybe I write it down here, I can kill eta, and this gives me Ku, and Ku mod the complex board element is precisely the integers. So this is a very convenient property for us which we use.
Cool, thank you.
Are you able to say or willing to say anything about the unstable chromatic homotopy theory involved when right? You have the connectivity, the index, how connective it is directly related to how, what the range of equivalences you have there. I assume that's coming from the unstable chromatic stuff.
Yes, so let me shortly comment on this. So the point is that, so applying B is maybe not the, so let's come in the first part, in this first step here. So this B is not so essential maybe, but so the GL, so just look at the simpler question that if we have a map from R to S, which we know to be an equivalence in some homology theory, we apply omega infinity to it and ask whether it's also an equivalence in this homology theory. And this is not true in general. And in particular, not for, say, Tn. And but there is a related notion of a Vn periodic, so-called Vn periodic homotopy groups, which are the same, well, essentially the same as Tn homology for spectra, but there are also corresponding notions for spaces, and their Vn homotopy equivalence and the Tn homology equivalence are quite different things, a priori at least. And it turns out this omega infinity sends a Vn homotopy equivalence to a Vn homotopy equivalence, and then there are these deep theorems which allow us to translate Vn periodic homotopy equivalence to this Tn equivalence in spaces. So this is the part where we really use this stuff. So we need, so these Vn periodic homotopy groups are, I mean, it's a little bit like a Whitehead theorem style, or maybe it's not Whitehead theorem. It's like, you know that if you have a map which is of spaces, which is an equivalence in homotopy groups, it's also one in homology groups. I mean, this is a non-trivial statement, but it's of course very classical. And this is a little bit similar statement in chromatic world. We have some chromatic analog of homotopy groups in spaces and some chromatic analog of homologies. And we need to go from the homotopy group equivalence to the homology group equivalence. And this is quite subtle here and uses all these assumptions.
Thanks.
I guess you might ask, I mean, do you have a feeling for what's missing to go, say, one step further in your proof up the towers?
You mean for the thing that the height is increased by 1?
Yeah, that's right.
I think the main point which is missing is that I mentioned that, so where did I mention this? Okay, I had this theorem here. And I said we can leave out the T0 information as well. I have a version just going from T1 to Tn, it's fine. But we are not allowed to just start at T2 because I had this counterexample with K-theory. And this is really the crucial point because we would really need a version which just starts at T2 and doesn't use any lower information. So this is the crucial point.
I have yet another question if no one else does. You were looking at the K1 localization of K-theory being homotopy invariant for ordinary rings. Have you checked for ring spectra with respect to either the flat or the free affine line?
So for the flat affine line, so if you have, I'm not quite sure what the most general theorem is we prove, but at least if we have something K1 a cyclic ring spectrum and use a flat affine line, is also homotopy invariant.
And then for the free one, it's not known.
For the free one, I actually think it's maybe also fine, because I think what we do is we reduce, so we use this truncating business so that at the end we can reduce to the pi0 of the ring spectrum.
Okay.
And I think if we just tensor with the free affine line, its pi 0 would be also just a polynomial ring in one variable. That should be fine.
Yeah.
But yeah.
There aren't more questions. Let's thank Lennart again.
Thanks, Lennart. Great talk.
And I'll stop
Thanks.
recording.
Thanks, Lennart.
Thank you,
Thanks.
Lennart.